We're talking about properties of solutions that are known as colligative. Okay, colligative means essentially collective. And what that means is it's for a collection of solutes, these properties will be true. It does not depend on the exact solute. It depends on only the concentration of the solute. Okay, so what's an example of a solution property that's not a colligative property, that does depend on the solute? Well, one example would be Henry's law. As you may recall, Henry's law says that the solubility of a gas in a solution will be given by a constant, K sub H, times the pressure of that gas over the solution. All right, so that constant, K sub H, does depend on a particular solute and solvent combination. It's different for every particular solute and solvent. So we're going to say that Henry's law is not colligative. But that's an example of one that is not. Okay, what are some ones that are? Well, they are listed here below. Vapor pressure, boiling point, freezing point, and osmotic pressure are all dependent upon solute concentration, but not on what the particular solute is. And before we go any further, the kinds of equations we're talking about in this film are going to be ones that involve non-volatile and non-electrolyte solutes. Okay, there will be a separate video that talks about electrolyte solutes, but this one is for non-volatile, non-electrolyte. Non-volatile means the solute doesn't have a significant vapor pressure, and non-electrolyte means it doesn't dissolve into ions. So an example of a volatile solute would be acetone. An example of an electrolyte solution would be sodium chloride. It breaks into ions. So we are talking about something like sugar. Or urea, or other things like that aren't volatile and do not dissolve into ions. All right, so let's first talk about vapor pressure lowering. The vapor pressure is lowered for a solvent if you add solute particles to it. Okay, and these little pictures help describe why that is true. If you have a pure solvent, like this little box on the left, you'll have collisions of molecules in the solvent colliding with the surface, and you will have collisions of molecules in the gas phase, if it's volatile, that collide back with the surface. And when it's at equilibrium, you'll have equal numbers of those going into solution and going out of the solution, maintaining a certain vapor pressure above the solution. If you add solute to that solution, we'll make our solute molecules as little X's in solution. Some of them will be blocking positions of the surface so that not as many molecules will be able to collide with it that are of the solvent. Okay, which means fewer of them will get into the gas phase. So you'll have fewer of them colliding back down, and your equilibrium position of vapor pressure will be fewer in the gas phase, again because there's solvent molecules in the way essentially at the surface. Okay, so this is lower vapor pressure. All right, and the vapor pressure of the solvent is given by Raoult's law, which is that the pressure of the solvent with solute particles in it is given by the mole fraction of the solvent times the pure vapor pressure. So let's put in pure solvent vapor pressure. And this is the mole fraction, chi, of the solvent. And then together they multiply to give the resulting new vapor pressure of the mixture. All right, so it lowers the vapor pressure. But we would like to have an expression in terms of the mole fraction of the solute rather than the solvent. So we're going to try rewriting this. Okay, we're first going to say that the solvent mole fraction plus the solute mole fraction has got to equal 1. In other words, if the solvent is 3/4 of the solution and the solute is 1/4, together they equal 1, as long as there's only one solute. All right, and then that lets us substitute into the original equation for P solvent. We can say that the mole fraction of the solvent is 1 minus the mole fraction of the solute, using the expression there. All right, and then it's times the pure vapor pressure from above of the solvent. All right, then we can distribute that P pure solvent, and we can get a new expression. We can say P solvent minus mole fraction of solute times pure vapor pressure of the solvent. And we're almost there. We can then take the pure vapor pressure of the solvent and subtract this vapor pressure, and that's a delta. Then a delta vapor pressure of the solvent, okay, the pure one minus the new one, is equal to then the mole fraction of the solute times the pure vapor pressure of the solvent. All right, and that will be our vapor pressure lowering equation, okay, because the delta, the change in vapor pressure, is the amount it's lowered. All right, try using that equation to solve the next problem. The vapor pressure of pure methanol, okay, this is using methanol as a solvent, is 101 torr. How much lower will it be if 2 grams of aspirin are dissolved in 50 grams of methanol? All right, so again, the solvent is methanol. So the vapor pressure of the pure solvent is this 101 torr. So what we really need is the mole fraction of the solute from this in order to calculate our vapor pressure lowering. All right, so let's do the mole fraction. The mole fraction of the solute is going to be the moles of the solute, which is the aspirin, divided by the total moles, which is the solute plus moles of the solvent. Okay, so the total moles on the bottom. All right, so what's the moles of the solute? Well, we're only given grams, but we're also given molar mass. So we can convert 2 grams divided by the molar mass, 180 grams per mole, would be the moles of solute. That same thing goes on the bottom as well. Plus another term for the solvent, and that is 50 grams over its molar mass, 32. Okay, so that gives us a mole fraction of 0.00706 of the aspirin in methanol, which allows us to feed into that equation we have in the box above. The change in vapor pressure is equal to mole fraction times the pure pressure, and that will equal 0.713 torr for our final answer. Now it turns out this lowered vapor pressure is what creates the next two colligative properties. Okay, and we'll illustrate this using a phase diagram. So how do solutes affect phase diagrams? Well, here's a phase diagram for water. It's a graph of pressure versus temperature, and there are these lines here that separate the different phases. The solid phase is in that section, the liquid phase in this one, and gas in that one. So this line represents melting or freezing, and this line represents boiling, or the opposite, which is condensing. All right, so if you're talking about, if you look at 1 atmosphere, which is normal atmospheric pressure, we can go across, and where that pressure hits this line is your freezing point for water, and that is 0 degrees. And where that line hits the liquid gas line is your boiling point, your normal boiling point. So that's your normal freezing and boiling point for pure water, and you know those numbers. All right, but what happens when you add a solute? Whoops, I guess I'm staying here. All right, when you add a solute, what happens is you lower the lines. Okay, you lower this line, and you to the left, and you change that line, and it shifts those two lines that are in equilibrium with the liquid over a bit, which means that now you have a new freezing point. Okay, there's your new freezing point. I'll put T sub prime, or T sub F prime, and it also means you have a new freezing point, or boiling point, T prime sub B. Okay, and notice the boiling point, the new boiling point in green, is higher than the old boiling point, so the boiling point is elevated. And notice the new freezing point is lower than the old freezing point, so the freezing point is depressed. Okay, and that will always be true. When you add solute to solvent, the freezing point will always be lower, and the boiling point will always be higher. So let's look at our expressions for those. First, boiling point elevation. And so you just have to remember that boiling point always goes up. It'll never be going down when you add solute. All right, so our second colligative property, the first one was vapor pressure lowering. Second one is boiling point elevation. And we can rationalize the boiling point goes up because there are fewer molecules in the vapor phase. Therefore, you need a higher temperature to boil. That's a T. All right, let's get back to black. All right, so you need a higher temperature to boil it. All right, and the expression for the boiling point elevation is the delta T sub B, the change in the boiling point. And it's always positive. Okay, it's always positive. Boiling point always goes up. And it's equal to a constant, K sub B, which is the boiling point elevation constant. And does it depend on solute? I hope you're screaming no, because this is a colligative property. It doesn't depend on the solute. It depends on the solvent. Okay, it wouldn't be a colligative property if it depended on the solute. All right, and then the final part of this equation is molality of the solute. So that gives the concentration of the solute in molal. And remember, molality is moles of solute per kilogram of solvent. So that's molality, and it's one way of expressing concentration. This boiling point elevation constant for water, which is probably one of the more common solvents, so I'm going to list it, is 0.515 degrees C per molal. All right, so that expression, it looks very, very similar to the one for freezing point depression. All right, freezing point depression, we can rationalize that because solute particles interfere with solid lattice formation. Okay, when you freeze something, you form a solid lattice, and so since they interfere with it, you must be colder in order to make that solid. When you have solute particles in there. All right, and the expression again looks very much like the boiling point elevation expression, except you have sub F for freezing instead of sub B. When you calculate freezing point depression, you will get a positive value, but you have to remember that you subtract it from the freezing point. Subtract it from the freezing point. All right, and this Kf is again the freezing point, the depression constant, and for water it is 1.85, and sometimes you use a 3 degrees C per molal, and again molality is in the expression as well. All right, so let's use these to do a calculation. Antifreeze, which is ethylene glycol, is added to water of car radiators so that on hot summer days it's less likely to boil, and on cold winter days it's less likely to freeze. Okay, because the boiling point is elevated and the freezing point is depressed when you add antifreeze. What are the boiling points and freezing points of the water with 3.62 molal antifreeze? All right, so we're going to calculate those kind of side by side, and with the two expressions. So the boiling point elevation is given by this expression, and the freezing point depression is given by a very similar expression. All right, so we know that the solute is water, sorry, solvent, not solute. The solute is ethylene glycol, and we know its concentration. So that'll be your molal. All right, so the boiling point elevation, this is water, so we're going to use the boiling point elevation constant of 0.512 that I just gave you, and multiply that by the molality of the solution. I'm going to set up the freezing point depression one at the same time. The constant for boiling water is, or sorry, freezing water is 1.86 degrees C per molal. And we have 1.62 molal. All right, so let's calculate those. We get 1.85 degrees C for the boiling point elevation, and we get 6.73 degrees C for the freezing point depression. All right, those are not our answers. Those are just the changes, but we want to know what are the boiling and freezing points. So we have to know where they started. Well, the boiling point of water, you should know, is 100, so you're going to add this to 100. So the new boiling point is going to be 101.85 degrees C. The freezing point of water is 0, so you're going, and you know this is a depression, so you're going to subtract from 0 degrees. Whoops, 0 degrees. So you're going to get the new freezing point is negative 6.73 degrees C. So when you add this concentration, 3.62 molal of antifreeze, you're going to raise the boiling point by almost 2 degrees and lower the freezing point by 6 3/4 degrees. The final colligative property we're going to talk about is osmotic pressure, and we're going to illustrate that with these drawings of tubes, 3 different tubes. The one on the left has a solution on the right hand side, and it has water on the left. Okay, so this is pure water. And on the right hand side is a solution of water with where X's are representing the solute molecules. Then in between the two sides we have a semi-permeable membrane, which is a membrane that allows certain things to pass through and not others, and in this case only water can pass. So the solute molecules can't go through it, but the water molecules can. So because the solute molecules are in the way, there will be a net set of collisions of water going to the more concentrated solution, to a certain point. Okay, it'll keep doing that until we get to a point where the left side is lowered and the right side is up higher. You'll still have your solvent on the right side, but water molecules will move into the section on the right with more solute. All right, and then we can look at that difference between the two heights, and that is our osmotic pressure, which we represent as a capital pi symbol. Okay, so that difference is the osmotic pressure. As a representation of the osmotic pressure. It will stop at a point where the collisions going each way are the same. Okay, and that will give you your pi. There's another way to represent pi, which I'm going to show in the third drawing, where you start with the middle drawing and you apply a pressure down the tube until you force the two levels back to being equal, like the original drawing on the left, and that force that you give to it is the osmotic pressure. Okay, so pi is also the pressure needed to equalize. All right, so that is what osmotic pressure is. How about some calculations? And the rationale for it is that solvent molecules redistribute until the collisions going each way equalize. Across the membrane. All right, and the expression for the osmotic pressure, this capital pi, is given by nRT over V, where N is the number of moles of solute, T is the temperature, R is the gas constant, and V is the volume. All right, so this looks a lot like the ideal gas law. It isn't about gases, but it is analogous to that kind of a pressure. All right, but we can look at this and realize that N over V is moles per volume, which is molarity when you're talking about solutions. So we can substitute that into the expression and get a even more useful expression that pi is the molarity of the solution times R times the temperature. So that is your osmotic pressure expression. Which you can use to do calculations involving osmotic pressure.